In this video, we're going to do some extra examples solving some differential equations. Okay, so the differential equations. The first one we're going to start with looks particularly intense, but it turns out to be something we've already done before. And it's the initial value problem because they give us this initial condition. So maybe I should just note that. So this thing here, this is the initial condition. So we know when x is equal to 1 that we should have y is equal to 8. Now, so our differential equation is here. So dy dx, so our derivative, minus 2x is equal to 2x over square root of x squared plus 3. So there's actually no y's here other than the dy dx. So this we don't need to separate the variables, although you could sort of use that method anyway. But if I move this 2x to this side, then I'm going to have the derivative is equal to some function of x. Okay, so that's one where we just needed to antiderivative. Okay, so let's just add 2x to both sides so that this one disappears. And then we're going to have dy dx is equal to 2x over square root x squared plus 3 plus 2x. Okay, so this is the form dy dx, or y prime, is equal to some function of x. So all we need to do is take the antiderivative to find y. Okay, so that means that y should be the antiderivative of this function. Okay, with respect to x. Now, because this is a complicated function, I'm going to split it up. Okay, so the first one here, the 2x over the square root of x squared plus 3, and then we can do that extra 2x ones separately. Okay, now this first one is quite complicated, but we can solve this using substitution. So for this one only, okay, we're going to use substitution. But for the other one, we don't actually have to. Okay, so my u is going to be the thing inside the square root, so x squared plus 3, which means that du is 2x times dx, right? The derivative of our substitution times dx. And I actually have that in my integral. Okay, so now I can rewrite the integral. So it's going to be 1 over root u times du. Okay, let me just emphasize that. Okay, so here's my u, and that's what I replaced there. So that's 1 over root u. And then the 2x dx is what I see right here. So that's equal to du. Okay, now the other one we'll just leave for now, but hopefully we know how to take the antiderivative of that one because it's quite simple. So now I probably want to rewrite this. So this is actually u to the negative 1/2 du in my antiderivative. And now I can use the power rule. So this is going to be, when I add 1 to the exponent, it's going to be 1/2. So this is going to be 2u to the 1/2. And then the integral of 2x is actually x squared. Okay, and then I have my constant of integration. And then, so if I put my u back in, I know that y is actually 2 square root of x squared plus 3 plus x squared plus c. Okay, so this here would be my general solution. Okay, so now what I want to do is find the particular solution. Okay, so we know that y of 1 is equal to 8. So that means that 8 should equal 2 times the square root of 1 squared plus 3 plus 1 squared plus c. So we can use this to solve for c. So 8 is going to be 2 times square root of 4 plus 1 plus c. So that's 8 is 2 times 2 is 4 plus 1 plus c. So that means that c has to be 3, right? Because 5 plus 3 is 8. So finally, our particular solution is y equals 2 square root x squared plus 3 plus x squared plus 3. So now we know what our c value is. Okay, let's try another one. So here we do have one that has both x's and y's in it. So we're going to use the method separating the variables. So we have dy dx is equal to 2x plus 3 times y. And we also have an initial condition here that y of 0 is 1. Okay, so what you want to be careful about is it's easier to separate when it's like this. So don't just go in and expand the y, because then it's going to be harder to separate the x's from the y's. Okay, so we want to just leave it the way it is. So if I multiply both sides by dx, say, then I have dy is 2x plus 3 times y times dx. Okay, and then I can multiply both sides by 1 over y, because that's going to get rid of this y over here. And I'm going to have 1 over y dy is equal to 2x plus 3 dx. And now I have all the variables separated, so I can integrate both sides. The integral of 1 over y dy, we should be comfortable now that that's ln y. And then when we integrate this, we can do it piece by piece. So this is going to be x squared plus 3x, and then plus our constant of integration. Okay, and so then if I want to solve for y, I want to use e. Okay, that's going to cancel out the ln. So this is going to be e to the x squared plus 3x plus c, which I could rewrite. So the constant doesn't really need to be up there, because I can write this as times e to the c, and e to the c is some other constant. So that means I could just write that y is e, oops, I want to put the constant in the front. So let's call it, I don't know, k. So k times e to the x squared plus 3x. Maybe I'll just make a note here. So k is some other constant that happens to be equal to e to the c, but it's just a constant, so it doesn't really matter how we write it. So this is the general solution. So we want the particular solution, so we know that y of 0 is equal to 1. So that means that 1 is equal to k e to the 0 squared plus 3 times 0. So that means that 1 is equal to k times e to the 0, which is 1. So we get that k equals 1. So if you would have left it the c, you would have got c as some ln of some value. So k is 1. So that means our particular solution is y, or absolute value y, is equal to 1 times e to the x squared plus 3x. Okay, let's try a word problem. So, suppose that the amount of yeast in a sugar solution grows at a rate that is proportional to the amount of yeast present. Okay, so it grows at a rate that's proportional to the amount present. And we know that there was 1 gram initially and 1.5 grams after 20 hours. So let's determine the particular solution for this. This is a differential equation. Okay, so let's just highlight some stuff here. So the rate, so the amount of yeast grows, okay, at a rate, let's say. So that's a rate, the rate that the yeast is growing. So let's let y of t equal amount of yeast in the solution. Okay, and then we know that y of, after t hours. Okay, so then we know there's 1 gram initially, so that means y of 0 is 1. And after 20 hours, we're at 1.5. Okay, so if y of t is the amount of yeast that the amount of yeast in there, then its rate is going to be dy dt. Okay, so this is the pink bit. Okay, and then it's proportional to the amount of yeast present. Okay, so that's actually y of t. So I'm just going to write it as y. Okay, and then the proportional bit. Okay, so this word proportional means that one of them is a multiple of the other. So I'm just going to call that for some constant k. So this is a proportionality constant. Okay, so it's just some number. So that's our differential equation. Okay, so we want to solve this. We actually did this already. Maybe I'll just do it quickly here on the side. So I'd move the y over. So I have 1 over y dy, and then I move the dt over is k dt. And then I can integrate. So that means that ln of y is equal to kt plus c. Okay, so then if I solve for y, it's going to be e to the kt plus c, which is actually, I don't want to use k again, let's call it y0. So some constant, e to the kt, where y0 is equal to e to c. So that's our general solution. Now we're going to use these two conditions to find our particular solution. So let's start with y of 0 being 1. Okay, because that's going to mean that 1 is equal to y0 e to the k times 0. So t is 0. So that's e to the 0. Okay, that is just 1. So that means that I know now y0 is 1. Okay, now if I use the other condition, so y of 20 is equal to 1.5. So that means that 1.5 is equal, so I would replace y0, I know that's 1 now. And now this is k times 20. So now I want to solve for k. Okay, so if I take the ln of both sides, e to the k, or to the 20k, ln of an e just cancels, so this is actually k times 20, which means that k is going to be ln of 1.5 divided by 20, which I computed to be approximately 0.02. Okay, so this means that our particular solution has both of those constants filled in. So the particular solution is y of t is equal to e to, you can use the ln if you want, but I'm just going to use the decimal here. So 0.02 t. So that would be our solution for this yeast. So now we can answer some questions about the yeast. How many grams of yeast will be present after 100 hours? Well, that's just y of 100. So that's going to be e to the 0.02 times 100, which we get 7.389 grams. Okay, now this one wants to know at what time will the amount have tripled. Okay, so that means that we want t so that y of t is equal to 3 times the initial amount. I'm just going to call that y0, which here is just 3 times 1. But you don't actually need to know y0, so I'm just going to show you. So if I didn't know what the initial amount was, then I would have 3y0 is equal to y0 e to the 0.02 t. And the first thing I would do is divide by y0, and it would cancel out on both sides. Okay, so I don't actually need that. So what I want to solve is 3 is equal to 0.02 t. So then we just want to solve it the way we solve for k. So I take the ln of both sides. So ln of 3 is equal to 0.02 t, which means that t is equal to ln of 3 divided by 0.02, which is approximately 54.93. So it will take approximately 55 hours to triple. Okay, let's try another one where we have some fixed maximum. Okay, so a certain nature reserve can support no more than n mountain goats. Okay, and we suppose that the rate of growth is proportional. So again, the rate of growth is proportional to how close they are to the maximum. Okay, so I'm going to let, maybe I'll let n of t be the number of, I don't want to use n, sorry. Let's call it m of t, the number of mountain goats. Okay, and then this initial condition that there were 1,000 goats initially, so we know m of 0 is 1,000. We know that the reserve can support, okay, so let's just write given over here. We know the reserve can support at most 4,000, so that means that n, capital N, is 4,000. And here the growth rate constant is actually 0.2, or 20%. So that's actually our K value. Okay, so this is actually the proportionality constant. Remember, they often call the growth rate. So maybe let's just highlight some more. Okay, so 1,000 goats initially is what gave us that. It can support at most 4,000, so that's our N value. And dark green. Oh, I haven't used regular green. No, I want that one. And the growth rate is 20%, so that's that. Oh, this is the one I wanted. I was like, why did I only use not that color? Okay. So this is what I wanted to be that color. Okay. So our differential equation is going to be that pink, yellow, green bit. So the rate of growth, that's dm dt. Okay. So that's the rate that they're growing. Oops. Is proportional, and we actually know the growth rate, so maybe this should have been yellow and green, dark green. So that's K, but here we know that K is 0.2. Okay, so it's also kind of dark green because they told us that. And it's proportional to how close we are to the maximum. So that's going to be our N, 4,000. So the difference between the maximum and what our population actually is. I'm not going to write m of t, I'm just going to write m to make things a bit easier. Okay, so that bit is from the green bit. How close we are to the maximum. So that's our differential equation that we want to solve. So we have both m's and t's, so we want to separate the variable, and again, be careful not to expand here because we want to move the m's over, and I don't want to do that by adding or subtracting. I want to do that by multiplying or dividing so that we're multiplied by dm. So it's easier if I just take this whole term over by dividing. I guess you could put this in, but you'd have to divide by the whole thing still. So it's easier not to. So what I'm going to do is multiply or divide both sides by, multiply by 1 over 4,000 minus m. Because then this part's going to disappear. Okay, so that gives me 1 over 4,000 minus m times dm. Okay, and I'm also going to multiply by dt to move it to the other side. So the t's are going to cancel over here. So then I'm going to be left on this side with 0.2 dt. So now I have all the m's on the left, all the t's on the right. So I want to integrate both sides. Now the integral on the left is a little bit harder. You might know what it is, but you might not. So maybe we want to use substitution. I didn't leave myself a lot of room over here, so I'm going to have to move it over a bit. But if we want to use substitution, the u is going to be the denominator, which means that du is going to be -1 times dm. Okay, so when we replace dm, we're actually going to replace it with negative du. Okay, so that means that this integral is going to become 1 over u times negative du. Okay, so the negative can come out front. And then I get negative ln, and it's ln u. I'm just going to put the u back in right away. So 4,000 minus m equals 0.2 t plus c. Now you want to move the negative over right away. Okay, so that means that ln of 4,000 minus m is equal to negative 0.2 t, and then the plus c doesn't matter. Okay, you can write negative c if you want. And then we use the e. Okay, so 4,000 minus m is e to the 0.02 t plus c, which you could write as, say, m0 e to the negative 0.02 t, like we've done. Let's just make a note. m0 is like e to the c. And then if we solve for m, I'm just going to go up here. So m is going to be 4,000 minus, m0 e to the negative 0.02 t. So that would be our general solution. Okay, there's one thing that we haven't used yet, and that is the m of 0 is 1,000. Okay, so let's use that. So m of 0 equals 1,000 means that 1,000 is equal to 4,000 minus m0 e to the negative 0.02 times 0. So that's e to the 0, that's a 1. So that means that 1,000 is equal to 4,000 minus m0, which means that m0 has to be 3,000. Okay, so that means that our particular solution is m is equal to 4,000 minus 3,000 e to the negative 0.02 t. Sorry, negative 0.2. When did I switch to 0.02? Somewhere here, right here is where I did it first. 0.02 was what we had in the last example. This one is just 0.2. Oops, this one is not times t, it's times 0. So this one here is our particular solution. And then we can use this to answer any questions they might have about this population. So for instance, what will it be in 5 years? So that's going to be m of 5. Okay, so that's going to be 4,000 minus 3,000 e to the negative 0.2 times 5. So this is 4,000 minus 3,000, and this e to the negative 1, okay, which is approximately 2,896 goats. So here they gave us a bunch of information. So we didn't have to compute the proportionality constant or the growth constant here. Okay, that was given. So just remember that when they say growth rate or decay rate, that actually is your proportionality constant. It will save you a bit of time if you don't have to solve for that. But this one is very challenging because of this sort of maximum idea. It's the integral we need to solve with in terms of m is a little bit more complicated. But there you go. So you can model different populations. There's all types of models. These are just a couple. It's a very interesting area of mathematics.